Homework 3. This homework is about second order reaction, the rate law and integral rate law. Question number 1. What is the difference between a first order reaction and a second order reaction? To answer this question, we need to look at the difference of the rate law and the integral rate law and their characteristics. So, the rate law for the first order reaction is Ka. The second order reaction is Ka squared, or Kab. The integral rate law for the first order reaction is natural log A over A naught equals negative Kt. For the second order reaction is inverse 1 over A, okay, minus 1 over A naught equals Kt. For type 2, it looks more complicated. The characteristics include the plot and the half-life. For the plot, for first order reaction, is the natural log concentration versus time is a straight line. For the second order reaction, is the inverse concentration with time is a straight line. Half-life for the first order reaction is independent of initial concentration. It's natural log 2 divided by K. But the second order reaction, the half-life is inversely proportional to the initial concentration. So it's 1 over K divided by A naught. Question number 2. It asks you to deduce expression for the time it takes for the concentration of substance to fall to 1/3 of initial value in a first order reaction and a second order reaction. So whenever it asks about time for the concentration change, we're looking at the integral rate law. For the first order reaction, the integral rate law should be ln A naught equals negative Kt. For the second order reaction, it's the inverse A minus A naught equals Kt. All right, so use this equation, you can calculate the time. You divide by K both sides, and you get this equation. And because the concentration falls to 1/3 of initial, so that means this is 1/3. Okay, and therefore you have plug in here, you should get at this point you should get negative 1 over K ln 1 over 3. All right, and this is negative ln 3, so negative, okay, it cancels, so negative K. All right, so the answer is ln 3 divided by K. For the second order reaction, okay, you want to calculate the time, you divide by K on both sides. All right, so you get this equation, and again this is 1/3 A naught. Okay, and then 1 divided by it, that gives you 3 over A naught. Okay, and that's why you have this one. 3 minus 1 is 2. Okay. In question number 3, it gives you the initial concentration and the half-life. It asks you to determine the rate, the order of the reaction, and the rate constant. Now, from the characteristics of the first order and the second order reaction, we know that for the first order reaction, the half-life should be ln 2 divided by K, which is independent of initial concentration. Now here, when you change initial concentration, the half-life also changes. That indicates this cannot be a first order reaction. Now second order reaction says the half-life should be 1 divided by K A naught. In other words, the half-life should be inversely proportional to the initial concentration. So from 9.72 to times 10 to the minus 3 goes to 4.56. The concentration reduced half. According to this equation, all right, the half-life should increase twice, and that's what we do observe. 328 increased to 85. That indicates this is a second-order reaction. To calculate the K, okay, we use this equation, half-life, and half-life is already known. Okay, we choose any of those data, and so the K can be calculated. Okay, for example, you can choose half-life is 328, then initial concentration is 9.72 times 10 to the minus 3. You can also choose the second data. Okay, should give you similar answer. Here is 0.314 per seconds per minute. In question number 4, it asks you to calculate the time for the concentration change. Again, we look at the integral rate law for the second order reaction. So second order reaction integral rate law is 1 over A minus 1 over A naught equals KT. Okay, from here we can calculate the time. However, there's a small thing we need to take care of. The reaction has 2 times A. Okay, as we mentioned in class, whenever there's a coefficient 2 times A, the reaction rate for A, or consumption rate for A, is twice the reaction rate, and therefore the rate constant for A, so Ka, should equals to 2 times the rate constant for the reaction. Okay, Ka usually sometimes write as K effective. All right, so here everything else is the same as we derived in class, the second order reaction. The only difference is the K. You need to times 2. Okay, and therefore time can be calculated. Okay, the only thing you need to pay attention is 2 times the K constant, and then 1 over a concentration, final concentration, minus 1 over initial. Okay, that gives you 1.24 times 10 to the 5 seconds.